Here we're looking at basic types of heat transfer, and we've talked about this before. These are ones driven by delta T. So if there's no temperature difference, there's no heat transfer, and it's also a function of area. So if you look at the mathematical equations for these three types of heat transfer, you have the delta T term in there, the temperature difference, as well as area. And conduction is where you have intimate contact with materials, and I showed you that flame example last class, and that's a function of the thermal resistance times the area times the temperature difference. Convection, number two, is a function of the fluid flow, whether it's a liquid or gas, so it has a convection coefficient associated with that, which is a function of velocity. And then finally, radiation, which also has an emissivity function, and it's looking at temperature differences to the fourth power, so you have to use the absolute temperature scale for that. And it had the Stefan Boltzmann constant as well. So those are three types of heat transfer in which energy is transferred, nothing else but energy. And big underlined energy there. And then we had these other two types of heat exchange, which I just reserved the word heat exchange for these because they're not involving only energy. The first one is mass transport, which is movement of actual physical matter. So the metaphor I gave you was of the open door. So if you open a door with cold air outside, the cold air comes inside, and those cold air molecules mix with the warm air molecules to change the total average temperature. And we call that infiltration also, which is more of the HVAC architectural term. So there's some overlap. Obviously, heat transfer is very important for environmental design. So there's a little bit of can be some different terminology. And you may recall when we talked about thermodynamics that energy is sort of this Gaussian distribution, or at least in terms of temperature measurement, it's a Gaussian distribution around the mean. So you measure the average temperature with the thermometer, but there are molecules that have higher and lower temperature values than that. And when you look at mass transport, that kind of is maybe a visual image to take in. So you've got this kind of group of 70-degree Fahrenheit molecules in the room, and you bring in a group of 0-degree Fahrenheit molecules in through an open door, and they mix. And pretty soon you end up with 60-degree average temperature molecules. So that's mass transport or infiltration. And that's, again, very, very important for a lot of environmental design issues, which maybe we'll look at later. And then finally, heat creation. So this is heat creation through chemical reaction, largely, whether it's in your body or through some exothermic reaction that creates heat energy by lowering the net energy of the products and combustors. So those are five, sort of like the normal and weird loads we talked about with mechanics and materials. These are the three, we'll say, normal types of heat transfer and two types of heat exchange, which are kind of analogous to weird loads that we talked about before. Obviously, they're all of equal importance. And the most difficult probably is radiation. So that's really what I wanted to focus on today. In heat storage, we talked about a bit with the SR-71 and the seatbelt buckle problem that you saw in the reading. But here we're talking about issues of specific heat, which is propensity of the material to respond to temperature or respond to energy. So if you impart energy into something, the heat goes up, and how much the heat goes up is a function of this intrinsic property called specific heat, and it's also a function of its mass too. So they go together. So if something has a high specific heat, it takes a lot of energy to increase the temperature. If something has a low specific heat, it doesn't take much energy to increase the temperature. And great examples of that are air versus water. So air and water have very different specific heats. I think air is 0.018 versus water at 1. Might be wrong on that, but that's roughly it. It's a big factor. And so if I have an open flame and I'm heating a bucket of air, it's going to heat up a lot faster than a bucket of water. And you know that just from personal experience, which is why we store heat energy and cold energy, chilled water systems, in water, because it's a really great material for that sort of thing. Because if you had to heat something up really, really, really hot to move energy around a building or your body or whatever, well, then you have all these problems with insulation. Because if you're, instead of running hot water in a building, you're running to heat up your baseboard heaters or whatever, you were running air. Well, you have to run that air up to say 700 degrees. And if you do that, you increase the delta T across things. Well, there's other like practical problems with that too, but one of them is you had these big high temperature differences. And the bigger the temperature differences, the higher the heat transfer. So as you're trying to move the hot air or cold air to where you need it, you're going to lose or gain heat that you don't want to do. So that's why water is a really good way to move energy around. And as far as this perception of why things feel hot and cold, that's a function of thermal conductivity in part. So if something's very conductive, as you draw heat away with your fingertip, or let's say cold, you're touching ice, as you draw the cold away, and I know the heat flows to cold, the second law of thermodynamics and all that, but just think about it anyway. As the cold gets drawn away, if it can get replaced by more cold very quickly, something's going to feel cold. So metal would feel cold in the plastic because the plastic warms up to your skin temperature very quickly, whereas the metal doesn't, because the metal keeps getting replenished by things that are colder than your fingertip. And with the bioclimatic chart, I might do that at the end because that's an interesting issue. I kind of want to get into thermal, into radiation right away. And this is an image you saw before. So these have really practical importance, and the most practical one, of course, is the sun, which is the source of energy for our Earth. And that energy does not come from conduction. It doesn't come from convection. It does not come from heat transport. It comes from radiation. And yeah, that comes from heat creation. Okay, that's where the fusion energy produced in the sun is the source of the energy, but the way it's transmitted to Earth is entirely radiation. So it's the one that we're most familiar with, and it's got a lot of cool layers to it. And that's what we'll explore here with the time we have before break. And these are just some visuals looking at absorptivity. So you recall that there are three properties associated with radiation. When something four, but incoming radiation is three. So when the sun strikes your face, it can do three things. It can transmit through your body, it can be reflected, or it can be absorbed. Those are the three things it can do. And we're not going to talk about albedo here because that's used a lot in climate studies and architecture. It's an important term, but I don't want to confuse things at all. So we're going to stay with those terms of absorption, reflection, and transmission, or the conjugations of those. And you remember we had those letters reserved for those terms. So absorptivity was alpha, reflectivity was rho, and transmissivity was tau. So those are sort of reserved terms. This is a shortcut. So here we're looking at absorption versus the color of the material for glass, metal, and plastic. So as you recall, black body radiator or black body is something that 100% absorbs energy. 100% of the energy gets absorbed, zero other gets reflected. So that's an ideal black body. And you can see to the right here, you've got this high absorption, 90% absorption, whereas clear or reflective materials have very low absorption. And that kind of makes sense to you. So something, that's why black things get hotter generally. And we'll look at some materials here. And you remember we looked at the picture of the Burke, or is it Chador, I guess, with the white towel over the top, how that changed the absorptivity of the material. So here's some numbers, okay? So if we look at absorptivity and reflectivity, you can see they equal 1. So for opaque materials, where the transmissivity is equal to 0, opaque, like a brick, absorptivity plus reflectivity are going to equal 1. And that's an important insight. And actually, as you know from the reading, absorptivity plus reflectivity plus transmissivity equals 1. So if something's translucent, then you can have all three of those things in play. So anyway, you see water. Now, there's a big issue here with frequency, which we're going to expand on just a minute. Let me just talk in general terms here. So water absorbs 90% of the energy coming in, and it reflects 10%. And then snow is 0.1 to 0.2, and it reflects 0.9 to 0.8. And you see these other different numbers for common materials that you see about us. And generally the absorptivity is very high, and the reflectivity is low. So we kind of have to watch again with frequency. You've been introduced to the idea of the difference between visible light and infrared light that we'll look at later. But if you look at the visible light spectrum for a moment, to be able to see something requires reflectivity. It's reflecting colors that are that upon which it's being irradiated. So if white light, which has all the colors of the spectrum, irradiates a wall, some of the colors get absorbed and some get reflected. It's kind of old physics stuff that you've heard a long time. But here is the spectrum. So what you can see is visible light is a small portion of the spectrum, and it happens to be the spectrum to which our photoreceptors respond. So it's a physiological issue. Beyond that, it has really no importance. It's super important for us because that's how we take in much of our world. But in terms of the science, it's not distinctive, I guess you could say. It's, in other words, energy is a function of Planck's constant times frequency. So the frequency or the wavelength, and those are a reciprocal relationship, are related to energy, and they have all kinds of importance for all sorts of things in terms of how they interact with materials and such. And it's a whole fascinating topic that we won't get into right now because we'll focus really on visible light and infrared. And in heat transfer, we're really looking at infrared, but we can't forget about visible light because it's such a part of our day-to-day experience. And we mentioned infrared. We think of this thermal heating. Visible light is things we can see, and then ultraviolet light is higher energy electromagnetic radiation that can cause degradation, so it kills things. So if you want to kill things, you irradiate it with UV light. And there's different ranges of UV light. UVC is a category used commonly for decontamination, so that might be in the press here soon. Who knows? Okay, so the energy budget that we encounter from the incoming radiation, and you've seen this before. So when the sun irradiates things, it doesn't do a good job of irradiating air molecules because there's so few of them. They don't interact with the photons from the sun very often, but the surface of the Earth does. Okay, it can't get out of the way. Bang, it's the surface of the Earth. And you have other issues too, like the moisture clouds, these sort of things that absorb solar radiation. And so when things, whether it be a cloud or the surface of the Earth, when it becomes irradiated, it has those three choices. It can transmit it through, which it doesn't if it's opaque, like the surface of the Earth. It can absorb it or reflect it. And that's what these red lines are. This is kind of the reaction of the Earth, as you can see, to this incoming radiation. And so when the sun goes down, the Earth is looking out into the dark night sky. It's really cold. All of the energy wants to go out to the night sky. And the only thing a couple things throttle it. One is the surface area. The other is the temperature difference between the Earth and deep space. But the big one is what's in the atmosphere. That's a huge one. So, and I think it's really neat because if those of you that have been in the desert at night, you know how bitterly cold it can get. And that's because the atmospheric brakes aren't on. So it often puts the brakes on the temperature of the air is the condensation of water. So once it gets cold enough that water condenses, that latent energy, if you remember, we looked at phase diagrams, to boil water, to melt water requires a lot of energy. So the temperature doesn't change, the sensible temperature doesn't change, but the latent energy increases a lot. So when it's getting cold at night, where we live, the water in the air is getting colder and colder and colder. And if it gets cold enough, if enough time evolves before the sun rises and rescues us from the bitterness of frigid evenings, we get dew, we get condensation with water. And when that water is condensing, the temperature is not going to get below the condensing point. So that's a wet bulb temperature. So if you look at the wet bulb temperature, and I won't go into this too much here because it's kind of getting outside the scope of what we deal with. But if you look at the wet bulb temperature prediction, that's going to be the coldest temperature you arrive at night. Because once you get to that, you start condensing water, and the temperature doesn't go down anymore. Well, in the desert, the wet bulb temperature will be very low. There's very little moisture, and so it gets colder and colder and colder and colder. And there's very little to stop it until the sun again comes up in the morning and rescues it. So if you reflect on that, I don't know how many of you have been in the desert, but if you have, that's why it gets so cold. And that was kind of a bunch of information there. I hope it's helpful. Okay, here's kind of the busy chart showing snow. And I want to look at snow in particular because snow is really weird. So if you think of mine stories, snow is a great mine story, just like the SR-71 seatbelt buckle. Because snow acts oddly. We know from our eye that it reflects light at visible light because we can see it as white. So this is this part right over here. So you can see the spectrum is on the x axis here. So here's snow, and we see it. It's white, and you know that from physics classes and color classes and all that kind of stuff. But then when you get into infrared snow, this heavy blue line, it goes way down. Okay, here we're looking at reflectivity. It's not reflective. It's not reflective, which means it looks, we'll say, black in infrared. Okay, and that's really important. It has all kinds of effects, and it's not intuitive. So now here's the twist. If you remember that snow is opaque, so there's no transmissivity, which means that big words here, just long words, they're not big words. It means that the absorptivity and the reflectivity are equal to 1. So if the reflectivity or the reflectance on this diagram is very high, it means the absorptivity is very low. And let's see if I can draw this thing. Okay, so here you can see it's very high. That's the reflection or reflectivity, which means the absorptivity is very low. But at infrared, that's this part here, infrared, it goes down very low, which means the absorptivity is very high. So if I have a plot over here of the absorptivity, and if, for example, imagine this side of the y-axis is absorptivity, well, this is how snow looks. It looks like this. And that's important to note. If snow is absorbing infrared energy, it's absorbing heat. Okay, absorbing heat. So it's a good heat absorber. And you can, I mean, what that means in practical cases might be a bit unique, but it's an important thing just to know, to highlight the difference in frequency or how frequency affects this reflectance and absorption. And I showed you another graph last class in which some materials like aluminum and such, they're kind of the same through a wide range of spectrum, which is interesting. But snow absorbs. But the thing with snow, of course, is a really good insulator too. So it has that effect. So snow can insulate things and keep things from melting. One of the things you'll see, maybe if you've ever seen the fallen leaf on snow, you'll see in some cases when there's a bright day that the leaf will work its way through the snow. And I have a picture of that. Actually, there might not be. Actually, no, they're not in here. I did it. Okay, that was something else. But if you look on a winter day, you'll see the leaf work its way through the snow because it's absorbing so much infrared energy. So just an interesting thing. So this graph, these are just factors. There's you can argue it, but these are the facts. And you see, like, water is quite linear too. You see the dashed line for water between infrared and the visible light. But snow is just kind of a remarkable anomaly. And we'll probably talk about that later. Now, this is the roof problem that we looked at a bit before. And I just wanted to expand on this again, just to review it. And this graph tells you a lot. And it's those of you that have been on a hot roof may have, you'll be able to make sense of this. And those of you that have maybe stood next to a wall that was really hot, if you were in a southern climate, and you walk by the wall, you can feel the heat radiating from the wall. You know, some of this might make sense to you. But here we're talking about noon, right here. And here's the outside air temperature, which peaks at about 1500 hours, I guess, okay, 3 o'clock-ish. And that delay between when the sun is at its strongest and when the air temperature is at its peak is this latency because of the thermal mass of the atmosphere. It takes a while for things to heat up. And if you recall too, the sun is irradiating the surface of the Earth, and the surface of the Earth is heating up the air. So there's some direct heating, but there's a lot of indirect heating from the surface of the Earth. So there's this kind of latency. And what I just wanted to focus on, because this is helpful, is look at the horizontal surface, which is this right here. So this is a roof. It's a fancy term for a roof. And it gets hot in the middle of the day. Okay, and you know that. If you don't know that, it does. And whoops. Oh. And okay, the slide shows over. There we go. Okay. And this temperature, sometimes called the cooling load temperature differential, term I like, CLTD, it's a function of not only the air temperature, so the roof is getting up to the temperature of the air, but it's also getting heated by radiation. So it has these two heating components associated. So the air is blowing over the roof, it's touching the roof, the air is heating the roof, but then the sun is heating the roof as well. And this is a light colored roof, and you might recall the dark colored roof is much, much hotter by about 40 degrees. But this is showing you a time element, which I think is interesting. So you have this lag. So the peak here is, say, 1 o'clock. Right? So it's sort of this, that's, except for the kind of scrawliness of my annotations. What's interesting here is you've got, you see the notion that the peak temperature is a little bit after noon when the solar radiation is the highest, and it's a little bit before the air is at its hottest. So you can kind of see both the air temperature and the radiation are working on this value right here. So if you understand, so here's a question for you. If you understand why the peak roof temperature is at 1 o'clock, you have a good idea what's going on here. And the answer is these are combined effects of radiation. So you have the air temperature heating up the roof and the sun heating up the roof. Okay, they work together. The sun peaks at noon, the outside air temperature peaks at 3 p.m., and they're both working together to get that roof hot. Now, again, this is for the light colored roof. Dark colored roof was much hotter. And then you'll notice too, the east facing roof here heats up earlier in the morning. And we'll stop here in about 5 or 6 minutes. Okay. There's the peak for the east facing. Here's the peak for the west facing. And you see the time difference because the sun is hitting them at different times. Okay, so again, this is the cure for, if you have the money, this is a cure for reducing cooling loads on commercial buildings. Well, commercial buildings throughout, well, most latitudes, but even residential down south. So you should change the color of the roof. It's a cheap and easy way. Well, it's not, I guess, easy for everyone to actually do it, but it's not cheap if you have to pay for it. But it's a easier way of cooling something than it is than having a larger air conditioning system. Okay, and this was the Hajib here with the white towel to reduce heat gain. And we talked a bit about how you can infuse black, if you want to keep the black color for religious purposes, there's a whole material science associated with that. So even though black normally absorbs a lot of thermal energy or infrared energy, you can change those characteristics. The SR-71 Blackbird, which we'll look at, we'll look at that later. And then the seatbelt buckle problem, again, those two are both in the reading, and we can review those. This one had a lot to do with specific heat. So remember, we went through that whole issue, and the answer as to why the seatbelt buckle gets so hot is because the specific heat of metal is so low compared to webbing, which is like coil, and it's much higher. And actually, just a brief summary with the SR-71, you remember the issue here was the only way to get rid of frictional heat. The only tool, the best tool in the toolbox was radiation. And so here we looked at emissivity, propensity to radiate outward. So to increase emissivity, you paint things black, and that lets things radiate heat better. And that was based, you can't change the area of this. You still have the flywheel. You can't change the temperature difference too much. because that's caused by frictional heating. This plane going 2,000 miles per hour. So you have very low air density, so convection doesn't work well. So you have radiation as the type of heat transfer you can use. And yes, you could dump the fuel. In fact, when it got refueled often, and the fuel was cool, so that helped keep it cool as well. But you didn't have much to work with. Yes, you could have some endothermic reaction going on in there that absorbs heat, but then you have a weight penalty for that. So anyway, it's not easy. It's and the good thing here is if you think of those 5 types of heat exchanges, conduction, convection, radiation, mass transfer, and heat creation, that's easier than what we did with mechanics of materials, where we had 11 different things. So we talked about this. So I'm skip that a little bit, and then we talked about breathing, how to keep cool naturally, and just as dogs do, if we can get rid of hot water, that's really good because water has a high specific heat, holds a lot of heat energy. If we can get rid of it by sweating or panting, that helps keep us cool. And we talked about the blood flow in large eared animals helping with that as well, and reducing area and all these sorts of things. So let's see. Okay, and there was that nasty equation, sort of, and it's kind of the ugliest equation we contend with, but it's all, this is radiation dealing with temperature. The big thing, I'll even raise my finger to emphasize the point, is these properties of the emissivity, absorptivity, and reflectivity, well, they are a function of the frequency. The frequency. So it's, and we can think in practical terms, visible light and infrared. That's fine. Infrared is heat, visible light is visible. So that is part of the mix there, and I think that's really important. And